Hi everybody, welcome to another video in Statistics, Chapter 5, Probability, Section 5.1, Probability Rules. First, we define probability. Probability is a measure of likelihood of a random phenomenon or chance behavior occurring. Probability describes long-term proportion with which a certain outcome will occur in a situation with short-term uncertainty. Right. So, of course, all the definition there, I let you read that. But we have, of course, the definition of probability, and now we have talk about outcomes, which is a result of some certain things. The long-term proportion in which a certain outcome is observed is the probability of that outcome. So later on we'll define something more concrete than just meaning of the word probability. Right. Probability will largely depends on the law of the large number. As the number of the repetition of a probability experiment increases, the probability with a certain outcome is observed get close to a probability of the outcome. So let's say we have a coin. If we toss that 3 times, we might have 2 heads, 1 tail, or 2 tails, 1 head, or 3 heads or 3 tails. But in the long run, if the coin is fair, we would expect to have 50% head and 50% tail. If we do that 3 times, it's not going to reflect exactly the probability. So the probability in that case will be 50% chance of getting the head and 50% chance of getting the tail. But that will occur if we do the experiment or we flip the coin a very large number of times. In that case, we will get close to that 50%. Right? If we flip the coin only 3 times, 4 times, the probability might not be close to the actual outcome, the actual probability of that event. Right, now, this is more important definition. So in probability, an experiment is any process that can be repeated in which the results are uncertain. Right, so experiment, so we don't know the result. Now with that experiment, even though we don't know the result, we can list all the possible outcomes. So that's what we call the sample space. So be all possible outcomes. An event is any collection of outcomes from a probability experiment. An event may have more than one outcome. Right. So in general, we denote the capital letter E or capital letter for the event. In the sample space, we use the letter S. Right. So let's look at a very simple example. If we an experiment of flipping a coin or tossing a coin, for example, the sample space will be either head or tail, and an event may be getting the head, for example. By the way, we use the curly bracket to list the set of all the possible outcomes for the sample space. E will be one or more in the sample space. Right, and look at another example. Consider the probability experiment of having 2 children. Identify the outcome of the probability experiment. So we have 2 children. The first child and then the second. Now, when we list like this, usually I go from right to left. So the second child could be a boy or a girl. But doesn't matter what we have on the second child. The first child might be a boy and a girl. So to list that, I'm going to have boy, boy, and then girl, girl, and then boy, girl. So the way we list is like this. We go from right to left, and we're alternating, we're changing between the outcomes on the first one. And then we go to the second one, we will interchange the outcome for every two of them. If we have another one on the left, we will alternate every four of them. We will do that eventually. But for now, the outcomes, all the possible outcome, we leave that, identify the outcomes. So the outcome will be just outcome boy, 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 girl, 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 boy, and girl, girl. The sample space will be all of this, all the possible outcome. Okay. Define an event of having one boy. So having one boy will be this or this. So we call that event. Could be having one boy, so could be a boy and a girl, and a girl and a boy. Yeah. So the sample space, all the possible outcomes, and an event have some of the outcome. Right. That's just simple but important definition. Right. Now before we go to do some calculation, a few more properties that we need to know. The probability of any event, we write probability of the event must be greater than or equal to 0 and less than or equal to 1. So we cannot have a probability that is more than 100% or more than 1, or less than 0 or negative. Any probability of any event have to be between 0 and 1. Could be 0, could be 1. And the sum of the probabilities of all outcome must equal to 1, right? So let's say we flip a coin, 50% chance get in the head, 50% chance of head in the tail, add them together, 100%. Or if we have a die, we can, with 6 faces, we can get 1, 2, 3, 4, 5, 6. The probability of getting each one of them, if we add all together, have to be 100% or 1. Right. Now, an impossible event has the probability of 0. So 0 is impossible and 1 is certainty. So impossible probability is 0, probability is 1, it's certainty. An unusual event is something that has a low probability of occurring, usually less than 5%. Right. Empirical probability, we won't be able to do that on the test because this involving experiment. The probability of event is approximately the number of times an event E is observed. So we have to do some experiment and then some observation, which we won't do that. Observe divided by the number of repetition of the experiment. Let's say we want to know if we toss in a coin, if we having a head or a tail, and we do that 1,000 times, and then we just record how many times we get in the head, and we divide that by 1,000. So that gives us the probability of getting the head for that coin and for that empirical probability. So that is done by experiment. We won't be able to do that in our problem. So what we actually would do is called the classical method of probability. So the classical method of probability will depends on will require that equally likely outcome. So for example, I just keep bring back to this, a coin, 50% chance of getting the head, 50% chance getting the tail. if we have a fixed cone and that have like 60% head and 40% tail, we cannot use that as a classical method. Or if we roll a die, the die has 6 faces, so there's a few things. So this is a die. Have 6 faces from 1 to 6, and if we use the classical method, this has to be a fair die, so the probability of getting each one face are equally likely. So an experiment is said to have equally likely outcome when the simple event has the same probability of occurring. So just like if we're rolling a die like this, the probability landing on one of the face have to be the same. Now, after that, if an experiment has n equally likely outcome, and if the number of ways that event E can occur is m, then the probability will be m over n, or we say the number of the element in the entry in the event over the number of outcomes in the sample space. So number of outcomes in the event divided by the number of outcomes in sample space. Right. Here is an example. Suppose a fun size bag of M&Ms contains 9 brown candies, 6 yellows, 7 red, 4 orange, 2 blue, and 2 green. And suppose that the candy is randomly selected. What is the probability that it is yellow, and what is the probability that it is blue? So we count. There are 9 brown, 6 yellow, 7 red, 4 orange, 2 blue, and 2 green. Alright, so that 15, 7, that 22, and 8, that 30. So there are 30 in total, right? 15, 11, 26, yeah, 30. What is the probability of getting the yellow candy? We know that's 6 yellow candies. So that's the number of outcome. In that event will be 6. There will be 6 candy out of the total 30. So this is called the classical method of finding probability. And the probability of getting a yellow candy is 6 over 30. We reduce to divide by 6, top and bottom is 1 over 5 or 0.2, or we can write 20%. There are different ways to write it. Next, what is the probability of getting a blue candy? There are 2 blue, so probability of getting a blue will be 2 out of 30, or 1 out of 15 if we reduce. And we have that 0.0667 or equal to 6.67%. So the answer may be in percent, fraction, or decimal. But be careful when we write the decimal. Make sure that we write enough decimal places. Right, more example. Suppose that there are 10 bones, number from 1 to 10 in the box. If one bone is picked randomly, find the probability that the number of the bone is less than 4. So first, if the bones is number from 1 to 10, if the bones are number from 1 to 10, the sample space therefore will be 1 to 10. And with that we can say the number of the outcome in the sample space n sub s is equal to 10. There are 10 of them. Next, find the probability that the number on the bone is less than 4. So less than 4, if we write the event less than 4 out of this will be 1, 2, and 3. So we say number of the outcome in the event E is 3. Because of that, probability of getting event E is just n of E over n of S, or 3 over 10. Of course, 3 over 10 we can write as 0.3 or 30%. Either way. So we can how many we have in the sample space and how many we have in the event, and divide by the number we have in the event by the number we have in the sample space. Right. Next, probability that the number of the mole is an even number. So the event now is an even number. Out of this list will be 2, 4, 6, 8, and 10. And if we count, there are 5 of them. So the probability of getting event E, event this, is the number in the event divided by the number in the sample space. 5 over 10 or 1 over 2, which is 0.5 or 50%. Right. So this is the most fundamental about probability. Next, we want a prime number. A prime number is a number that divides by 1 and itself. So 1 is not considered to be a prime number. So 2 divide only 2 and itself. Same thing for 3. 4 is divisible by 2. 2 is not 1 or itself, so 4 doesn't count. 5 is 6, can divide by 2 and 3, so it doesn't count. 7, not 8, not 9, because 9 is divisible by 3. Right, so we have only 4 here. Not 9, not 10. So we count and there is 4 of them. So the probability of getting this event a prime number is 4 over 10, which is 2/5 if we reduce, or we say 0.4 or 40%. Right. Right. So like I said, the most fundamental about probability is just list all the possible outcomes and assume that they have equally likely outcome. Then we just count how many we have in the sample space, how many we have in the event, and we divide them. So that's pretty much it. Next, what is the probability that a couple has 3 children with no twins and 2 of them are boys? Actually, twins are a dozen. Let's assume that less complicated things, so there's no twins. Right, so there are 3 children. Remember, this is kind of like what we did earlier. So we have first, a second, and then the third. Right, like I said, the one on the right will alternate every one of them. The one on the left, the next one to it will alternate every 2. The next one will alternate every 4. The next one will alternate every 8. So just power of 2. Right? So every one, I just write in pencil here. This will alternate every one of them. And then every 2. And then every 2 square, which is 4. Then 2 cube, which is 8. And then 2 to the 4th, which is 16. Just multiply by 2 when we go from right to left. Right, so now we alternate every 4. So we have to have 4 of them. And then 4 of the other. Right. Next, the next one we alternate every 2. Yeah, alternate every 2. And if we do like this, it will not be repeated. And the last one we alternate every 1. So if we do this, they will not overlap. So there will be 8 different outcomes here. So the problem here is find the probability that 3 children and 2 of them are boys. So 2 of them are boys. So first we'll give the sample space. I'm just going to write this. There's 8, and we say the number of in the sample space 8. Actually, yeah, we used the capital letter earlier, so we just use that. Now in the event, this event, 2 of them are boys, so 2 boys. So we look over here, and exactly 2 boys. This is 1, 2 boys, 2, not that, this, not that, not that, not that. So there are 3 of them, and let's list them. And then number of outcome in that event is 3. So the probability of getting that event of 2 boys is 3 out of 8. 3 divided by 8, 3.375, I think. Yeah. Or we say 37.5%. Yeah, just move, let's move places, 2 places to the right, to the left, and then add the percent. If we move to the, move to the right and then add percent, 2 places to the right and then add percent. If we move to the left, we move the percentage. Right, next, the subjective probability of outcomes is the probability obtained based on the personal judgment. Usually that will not be the one that we do a lot in this class. So an economist predicting that there's 20% chance of recession next year. That could be a probability, subjective probability. Also, another example of this is the Interchange magazine. So before, let's say, when we're betting on the horses to win a race, usually depends on the popular of the horse or something. The probability of the horse winning the race, those are subjective. And actually, not only based on that, if a lot of people betting on a certain horse, the chance for that horse to win, the probability, the odds will change reflected to the actual betting. So that of course is called the subjective probability, will based on the personal judgment, maybe of one or many people. Right. So this section, the most important is the classical method of finding probability. First, we list every outcomes for the sample space, and then we find how many outcomes we have in the event, and then the probability of the event is just dividing how many we have in the event divided by how many we have in the sample space. Right. Second section, addition rule and complements. So addition meaning we add. two events are disjoint or mutually exclusive. Those two mean the same thing. If they have no outcomes in common. Suppose we randomly select a chip from the back, and each chip with label from 0 to 9, so that 10 of them from 0 to 9. Let E be the event of choosing a number less than or equal to 2. Alright, so let's write E is less than or equal to 2. So in that case have to be 0, 1, and 2. And let F be the event of choosing a number greater than or equal to 8. Greater than or equal to 8, so 8 is okay, and greater than that, so 8 and 9. So are these events mutually exclusive, or are these events adjoint? And the answer is yes, because they have nothing in common. E and F have no common outcome. Find the probability of E and probability of F. So probability of E, there are 3 in E and there are 10 in total. So we have 0.3 or 30%. Probability of event F, there are 2 of them out of 10, which is 0.2 or 20%. Now, find the probability of E and F. Now, because E and F, meaning that it has to be in both of them, and since they have no common outcome, E and F cannot happen. E and F, if we write like that, the set will be an empty set, or we use this for an empty set, because they have no common outcome. So because of that, probability of something that have no outcome out of 10 is 0 or 0%. And next, find the probability of E or F. E or F meaning it could be in E, it could be in F. So it could be one or the other, could be both as well, but we know that it cannot be both. So P of E or F, so we say E or F can be either in E or could be in F. And the probability of that, there are 5 of them out of 10, or 1/2, or 0.5, or 50%. Right, so be mindful with the word and, meaning they have to be in both of them, and or it could be in either one of them, or could be both, or mean also include the case when there's both. So addition rule, so it says that if E and F are disjoint or mutually exclusive, then the probability of E or F is equal to probability of E plus probability of F. As you see, the probability of E is 30%, probability of F is 20%, probability of E or F is 50% when we just add these two together. Now, that is when they are mutually exclusive or disjoint. If they have something in common, then the rule will change later. But for now, this is for the disjoint event. We just add them. Maybe not just 2, maybe more than 2 events. We can just add them. Right. A standard fair die is rolled once. So a die, once again, is a rectangular cube that has 6 faces. Label from 1 to 6. Find the probability of getting an even number. So we list there are 6 faces, so the sample space will be simply 1 to 6. And this is a fair die, so equally likely. Even number is 2, 4, and 6. The probability of getting an even number, therefore, will be how many we have in here divided by how many we have in there. 1/2, 0.5, or 50%. Next, find the probability of getting a 1 or 6. 1 or 6, of course, it is 1 or 6. So the probability of getting this event will be 2 out of 6. And you see at this stage what we do is just strictly counting. This how many we have in the sample space, and then how many we have in the event. So that is when we have the mutually exclusive event, like getting a 1, getting a 6, are mutually exclusive. Right. Next we have the general addition rules. For any 2 events, E and F, so this could be disjoint or not. In general, the probability of getting E or F is equal to probability of getting E plus probability of getting F minus the probability of getting both. Right, here's an example. Suppose that a pair dice are thrown. Let E be the first die is a 2 and F be the case of the sum of the dice is less than or equal to 5. Find the probability that using the general addition rule. Right, now we have 2 dice. 2 dice, a pair of dice. So the first die I'm gonna do like this. The first die could be 1, 2, 3, 4, 5, or 6. The second die could be 1, 2, 3, 4, 5, or 6. Now, I'm going to list everything here will be 1 on the first one. And the first one is 1. First one. And first one. Right. And then on the second one, the second, just put a comma in between them. Right. The second die could be, now I write everything in column 1, 2. So this is a systematic way to list everything out. That will be no overlapping. So you see each outcome will be equally likely. Now, next, let A be the event of the first die is a 2. So the first die is a 2. We have here So there. By the way, let's count how many we have in total. There's 6 rows, 6 columns. 6 by 6 will be 36. So the number, let's use the capital letter. In the sample space, there are 36 of them, 36 outcomes. Right, let E be the event. The first die is a 2. The first die is a 2. We have 6 of them. Have 36, which is 1/6. Now, the F be the sum, be the event that the sum of the dice is less than or equal to 5. So less than or equal to 5. So the thing about this, when we list the table like this, everything in the diagonal will have the same sum, right? 2 plus 1, 1 plus 2 is 3. Now this 3. 3 plus 1 is 4. 2 plus 2 is 4, 1 plus 3 also 4, so everything in this case, right? Now, and everything less than or equal to 5, so we have to have less than or equal to 5, right? So if we list them, less than or equal to 5, be less than just mark this. So the event F is the sum of the dice less than or equal to 5. So those are less than or equal to 5 will be 4, 3, 2, 1. Add them together is 10 out of 36. If we reduce, actually just keep it 10/36. Or we reduce by 2 will be 5/18. Actually, it's much better just keep over 36. And then, what is the probability of getting E or F? Now, if we count, this is 10, right? 10 in this, and then the event E have 3 more, so we have 13. If we just count, that will be 13 out of 36. Simply just count. Right, so that is the classical method. Now, but they said using the general addition rule. So general addition rule is probability of getting E or F equal to probability of getting E plus probability of getting event F. Subtract the probability of getting event E and F. So we know the probability of getting event E is 6/36. Just keep that, so it's easy to add them later. And then F is 10/36. And then minus E and F. E and F, the overlapping of those two will be 1, 2, and 3. So minus 3 out of 36. Now since all of them have 36 at the bottom, we can combine the top. 6 plus 10 plus 3 minus 3. So notice that adding fraction with the common denominator, just keep the bottom, the denominator, and add the top. So 6 plus 10 is 16 minus 3, so 13/16. So we use the general addition rule. That will get us the same thing as just classical method. Just count how many we have. Right, next, the table lists the ranking habits of a group of college students. If a student is chosen at random, find the probability that of getting someone who is a man or a non-drinker. So we have a man, non-drinker, regular drinker, and heavy drinker. All of them add up is 187. A woman, 187 plus 21 plus 10 is that. And then if we add all the non-drinker, all the regular drinker, and all the heavy drinker. So the question is, find the probability of getting someone who is a man or a non-drinker. The key here is all here. Right. So actually, when we have a table like this, or what we did earlier, it's much easier just if we can count. For one thing, the total is 405, and this is the number of the sample space. And then the question is probability of getting a man or a non-drinker. So we just count a man 187. Actually, I'm going to just put this. That would be a man. And non-drinker, I'm going to add this. I'm not going to check the total number though. So, and then we just add how many we have here in each little box. 135 plus 47 plus 5. We not use the total because the total is not a category. It's just a total of things. And 187, 374, 405. So I have about 0.9, 3, 4, 5, 6, 7. Interesting. 3, 4. So that's about 92.34%. If we round, that would be 5. Right. Now, so that is by counting. If we use the general addition rule, a man or a non-drinker will be equal to probability of selecting a man plus probability of select a non-drinker minus the probability of getting both, meaning a man and a non-drinker. Right, let's count. How many we have as a man? A man total is 187 out of 405 plus probability of non-drinker, that will be 322 out of 405, and then subtract that is both a man and a non-drinker is 135. Once again, we have the common denominator 405. I'll just add the top 187 plus 322 minus 135, and we have 374 divided by 405. Right, so that's what we have. Here's another example. A card is drawn from a standard deck of 52 cards. So it's like this. Find the probability that the card is a queen or a club. A queen is this. There are 4 of them. And then a card we have 4 suit. And this is a club. And it's a spade, heart, and diamond. Right, 4 suits. These 2 are red, the other 2 are blacks. Right, now we have either 5 probability of a queen, which is these 4, or a club. A club is the first one. So if by simply counting we have that 13, 14, 15 and 16, so the probability of getting a queen or club is that's 13 and 16 out of 52. Reduced by 4, we have 4 over 13. About 0.3077 or 30.77%. Right, so we just count. Always use the general addition rule. 4 out of 52 plus 13 out of 52 minus the one that's both will be 1 out of 52, and the same thing. Right, next what we have is called the complement rule. Complement is, so let S denote by the sample space of a probability experiment, and E denote an event. The complement of E denote E with the superscript C, so the complement its own outcomes in the sample space that are not, so the complement meaning not in event 8, right? Because of that, the probability of a complement event is just equal to 1 minus the probability of getting that event. Here's some example. According to American Veterinary Medical Association, 31.6% of American households own a dog. 5 probability that the random selected household does not. So does not meaning not getting a dog. So first, from the prompt, getting a dog is 31.6%. So the complement rule, the probability of not getting a dog is 1 minus the probability of getting a dog. So we have 1 minus, I'll convert this to decimal. Uh, 0.684. Or 68.4%. Now, next one is a little more interesting. A fair coin is tossed 3 times. Find the probability of getting at least 1 head. Right. Do this a couple ways, 2 different ways. If you recall the problem where we have 3 children, a boy and a girl. So again, we consider the likely outcome of getting a boy and a girl. And same thing here, a fair coin, we assume that it's also a fair coin of getting head or tail. So if we list them, the first one, second, and then third. Right, the first one will be every 1, every 2, and every 4. 1, 2. We're talking about corn, right? Head, 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 tail, 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 tail. Second one would be head, head, tail, tail, head, head, tail, and tail. The third one would be alternating every 1, head, tail, head, tail, head, tail, head, tail. So if we do this, it will be non-overlapping. Find the probability of getting at least one head. Wow. So that will be at least one head. There's a head, there's a head. So if we count, there will be 7, right? At least one head will be 7 of 8. So if we just simply by counting, probability will be at least one head. There's 7 out of 8. Right, if we just count. Now, if we don't want to do that, we just take a look. When we say at least one, the complement to at least one is going to be what? Be none, right? At least one could be 1, could be 2, 3, 4, 5. I mean 1, 2, or 3 in this case. But what it cannot be is 0, right? So first we write this 0 head and at least one head are complement. And we say complement event, and then you say, wait a minute, they have nothing in common, right? So why don't we call them mutually exclusive? First of all, they are mutually exclusive, but moreover, not only they have nothing in common, that's for sure, but the total of them have to be equal to 1, right? So, for example, if we said the probability of getting 0 head or the probability of getting 1 head, those two are mutually exclusive, but they are not complement. Complement meaning if it's not in there, that will have every other outcomes, right? So if it is not the last one, when there's no head, it will have at least one head, right? So those two together will be all the possible outcomes. So that's what we call the complement event. So it's not just mutually exclusive where they have nothing in common. Complement, they have nothing in common, and when you put them together, that will be the sample space, right? Because they are complement event, we can use the probability that we said, probability of at least one head is equal to 1 minus the probability of the complement to that, which is 0 head, and 0 head will be the last one, so 1 minus 1 over 8, and that is 7 over 8. If we use the calculator, 1 minus 1 over 8, and then we can convert to fraction. Right, so complement event, very nice. We don't have to count as much. Next, find the probability that the sum of the dice is 11 or more. So let's go back to the dice. We have on page 66 here the die, and there will be 36 outcomes. So let's just write out again. 2 fair dice are thrown. The number of sample space will be 36. 6 by 6, 36. Find the probability that the sum of the dice is 11 or more. So 11 or more. So it could be 11, could be more than 11. So this is 6, 5, 5, 6, and 6, 6. We only have 3 of those. Right. So to get the sum of the die to be 11 or more, let that event be A, and probability of that is 3 out of 36. 1 out of 12. Right? Because the event A, if we're going to list them, 5 and 6, 6 and 5, and 6 give us 12, which is more than 11. So there are 3 of them have 36. So 112. Find the probability that the sum of the die is at most 10. Right. So same thing. At most 10. So it could be 10 would be the most. Anything less than that. So it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But of course we don't have 1. The smallest one is 2. 1 plus 1. We have 1 on each die. Right? So if we're going to count, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm sorry, there's no 1, so it'll be 2, 3, 4, 5, 6, 7, 8, 9, and 10. It cannot be 11, cannot be 2. So if we want to list out all the possible outcome, I see the sum could be equal to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. The event of getting 11 or more will be these two. And then the complement to that will be anywhere from 2 to 10. So that will be at most 10. Right? So they complement to each other. So rather than we count everything we have from 2 to 10, of course we can count them manually. But the best way to do it using that properties, probability of at most 10 equal to 1 minus probability of the complement event. Of that will be 11 or more. So we have 1 minus 1 over 12. That will be 11 over 12. One minus 1 over 12. Right. Convert to fraction. It is 11 over 12. Right. Before we do that, it's nice to write that at least, at most 10 and 11 or more are complement event. Because of that, we can use this formula. So here's a few things here. Some terminology that we need to know. We say at most. That means will be less than or equal to. At least will be more than or equal to. And we can have less than or no less than, more than or no more than. Of course, that would be just greater than without equal. Right. At most, it could be that number or less. At least could be that number or more. Right. I want to end this section with a classic probability problem. It's called the Monty Hall. Monty Hall is the game show in the, I think in the 80s. So the game is like this. There are 3 doors. One of them is the winning. When winning, there's a car, and the other 2 doors, you're not winning. There will be a goat. Right, let's see, we have, this is the winning, and when you get one of those, are not winning. So what I do is, of course, I will scramble the order, and I know exactly where it is. And ask you, pick which one you think is the winner. let's say you choose this one. So what I do as a host, and the host, it will be a classic case will be the Monty Hall himself. What he does is, instead of open that door for you, he open the door that is not winning. Once again, he opened the door that is not winning, because he knows exactly which one is winning, which one's not. And the question is, do you want to switch your choice now before you open it? And that is the game show. It's of course much simpler than the Deal or No Deal or any game show right now. But the point here is, it's not that do we switch. The answer here interesting in statistic is that should we switch our choice to here before we open it, right? Now, statistically speaking, we should switch every time, because when we switch, the chance for you to win will be double, right? So now if we switch our choice and then we open it, and that is the winning choice. Right, let's recap. There are 3 of them, and when we scramble, the host knows exactly which one is it, and then you can choose one, and then the host will open a one that is not a winning choice, and the question is, should we switch? Right, now let's look at this a different way. Let's say there are 3 cards. One of them is winning, right? One of them winning. We know now this one is the winning. If you don't know that, you pick one of them randomly. What is the chance you think is going to win? If you don't know anything about that, the chance for you to win is 1/3, right? 1 out of 3. Now, by reviewing this card doesn't change the probability. You still have 1/3 from the beginning, right? Now, you still have 1/3. When I show you this card, it's still 1/3. But if you switch your choice, then your chance of winning will be double. Why is that? Originally, the chance of winning when you choose this card is 1/3, right? It's 1/3. When you switch to this, you switch to the complement of it. Because if originally is the winning, when you switch, it will be not winning. Or if the original one is not winning, when you switch, it is winning. So you can only choose one of those 2 cards. Now when we switch, originally you have 1/3 of winning. When you switch, the complement to that will be 1 minus 1/3, which is 2/3. So when we switch, the probability of winning will be double, and so because of that, we always switch. I'll leave you a link here if you want to read more about that. But that's all I want to cover for these 2 sections. See you in another video in statistics.